power in my MATLAB here. So how could I be sure that this bit difference is meaningful? I'm just going to be throwing a lot of data. I'm just throwing a lot of data at my very simple algorithm, and I hope the statistics helps me. That's all I can tell you, right? This is a statistical method. If you use enough data, you can hand wave away all the complications. Sometimes you can do it, and then you need to do something more complex, but you can read the book about it. So now, and just type in your questions. Oren Gil. To assume that the errors have one mean, and the right answer has. I'm assuming that the power consumption is a function of the data. That's all I'm assuming. And I'm assuming that I can guess one bit of the data. So the power consumption is a function of this one bit, which I guessed. So if the power consumption is a function of the data, and I guessed one bit of the data, then I can split my traces into two sets. It's very minimalistic, and of course I'm throwing away a lot of my knowledge on the device under test. For example, I'm throwing away the Hamming weight model assumption or the Hamming distance model. I can't use it because I don't know how to. I don't have statistical knowledge to do it right now. I can do it with CPA, but I won't be teaching it this year. Okay, let's look at the results, and this is a nice way to understand what's going on. So my input was d times t, right? D data points, each one of size t, right? And we tried fixing, fixing d and fixing t, and I showed you that if I fix d, I get one trace, and if I fix t, I get what all the devices were doing at a certain amount of time, a certain period of time, and I aligned this perfectly. Now, I calculated 256 different ways of splitting my traces into two. Right? What does it mean, way of splitting the trace into two? It means one bit value for each one of the traces. Right? So if I'm saying data 1 and 3 and 5 go into bin 0 and 2 and 4 go into bin 1, then my hypothesis is going to be bin 0, bin 1, bin 0, bin 1, and so on. I need to assign each one of my traces into a bin. So a single hypothesis is a vector of size d, which assigns each one of the traces to a bin. I have two bins, right? I have 256 possible ways of splitting into bins because I'm trying to guess one state byte at a time, right? So if I fix a row in this matrix, a column in this matrix, to say if I guess that my key byte, for example, is I don't know 5, then this is the split which is going to be derived from this assumption. So I'm going to assume that if I fix 5, then these traces go to the left bin, and these traces go to the right bin. So I have 256 different ways of splitting the traces. Now, for each one of these ways, I can calculate the distance of these. So I say, okay, I guess that the key is going to be 5. Now I have two bins. I threw half of the traces into one bin and half of the traces into the other bin. Now I calculate the mean inside this bin and the mean inside that bin. Because I didn't put scalars inside the bins, I put vectors, my mean is also going to be a vector. So I have the mean of all the traces in the left bin and the mean of all the traces in the right bin. Two vectors. And now I calculate the distance of means, and the distance of means is also going to be a vector. So I have a vector which says if the key guess was 0, this is the distance of mean. If the key guess was 1, this is the distance of means, and so on, all the way to if the key guess was FF, this is the distance of mean. So I have an array, 256 different guesses, and t different points of time. So when you are going to be reviewing this at home, if you understand why each one of these data structures has this size, you're in very good shape. It means you've understood DPA. So you should be very pleased with yourself, because this is a complicated subject. And if you understood it, you'd be very, very pleased with yourself. Since you're watching this in a recording, I guess this is the time where you should be pleased with yourself. So bravo. If you're in class right now and you understood it, I'm actually surprised. Maybe you'll learn it somewhere else. But this needs revising. You can revise using the videos. You can revise using the book. And you can revise using the handbook from last year also. Right. So now I'm going to show you this output, this 256 times t, this difference of means vectors, and it was calculated by the authors of the DPA book. This is a figure from the DPA book. Now let's look at this figure together. So the x-axis of this figure is the time, right? The y-axis is the difference of means. And each one of the lines in this graph is a different key hypothesis. So what the authors of the book did was they overlaid these 256 different figures on top of each other. And let me just see. I didn't want to do it. Right. So all of the incorrect key guesses are in gray, and the correct key guess is in black. So does everybody understand what is illustrated in this figure? Who understand what is shown in this figure? I told you, I'm happy to teach less material and teach it well this year. So 6 people answered. 9 people are what? Doing yoga during class. Who understands what is illustrated in this figure? Not what is the correct thing. Who understands what is illustrated in this figure? I have 6 people responding, and 9 people, I don't know what they're doing. They're doing a workout video. I don't know what they're doing. Walking the dogs. I don't know. So one of the people just quit the presentation because there was so much pressure to answer the poll. Fantastic. Okay. I'm going to explain this again. And this is the most difficult material in the course. You understood this, you're in great shape. The x-axis is the time. This measurement was taken over hundreds of thousands of points in time. And the y-axis is the difference of means. So I guessed the key. I split my measurement set into 2 piles. I calculated the mean of this pile, the mean of that pile, and I subtracted the 2. So if I did a meaningful split, I hope to get a peak somewhere. And the black means the correct key, and the gray means all the incorrect keys drawn one on top of the other. And now looking at the figure, you see that most of the time we get a very, very small difference of means. It's around, this is the sum of many, many random variables, so they really tend to stay inside this area around 0. So this is measurements of 0 with noise. The distance of means effectively is 0. But you see that for the correct key, there is an area where you have a really, really significant difference of means between the 2 bunches of traces which I created. What is the meaning of this? It means that this is the correct time. During this time in the computation, the device under test was indeed processing this state bit, the state byte. It was indeed processing the bit which we guessed, and we guessed it correctly. And this means that in this period of time, this specific time, we got a peak. So this means this is the correct key. All the other keys, we didn't get a good split because we were dividing our measurement into two sets, which were essentially the same set. So what else can we see here? Yes, Oel, you have a question? Yeah, there is gray behind. Okay, so right, two phenomena I'd like to point out in this graph. There are two interesting phenomena here. One of them is that there are grays here. We try to zoom in even more. There are gray peaks here which are almost as powerful as the black peak, right? This is one thing we should notice. And the other thing you should notice is that there is like a period here where the incorrect key has peaks and the correct key doesn't have peaks, right? What are we seeing here? Effectively, our power model wasn't very intelligent, and it looks like there was an incorrect guess, which also got us a peak. This is called the ghost peak. Why is this? One possibility is that we were actually looking at the inverse of our guess. So, you know, when we're using a microcontroller, first the bytes are loaded in, and then they're loaded out. So you're also getting the complete inverse. You're also getting peaks on that. And it could be that you're not very powerful, you're not very good in rejecting traces. So if you recall, one of Stefan's graph from last week was the x-axis was the amount of traces, and the y-axis was how good was the correct key in comparison to the incorrect key. So when you're adding more and more traces, hopefully you're going to be able to reject the incorrect key well. But indeed, this is a problem. You have ghost peaks, and you have incorrect key guesses getting right. So you might need to do some post-processing, even though your statistical method, you might have several key candidates. You might need to reject